All right, everybody, welcome back. Today we're going to talk about electronegativity and dipole moments. We'll define electronegativity and dipole and use that to talk about polarity, and then we'll use electronegativity differences to determine if a bond is ionic, polar, or nonpolar. So two terms we'll define: electronegativity and dipole. If you remember from before, we talked about electronegativity as being the ability of an element to attract electrons within a covalent bond. And so what we found is that electronegativity increased as we went up the periodic table and as we went to the right on the periodic table. So our most electronegative atom was fluorine. And so it really wants to hog the electrons and steal them whenever it's in a bond. When we've talked about bonds, we've talked about them as looking at metals and nonmetals being ionic, which we will still continue to do, and then two nonmetals forming a covalent. In actuality, bonds have just kind of a character, so they'd be more covalent in character, and that's what these triangles are showing here. So we're looking at bonds that are just more covalent in character. So a bond that has an electronegativity difference that's very small is going to be more covalent in character, and then if an electronegativity difference is big, then it will be ionic. Now, if we define this, we would say 0 till about 0.4 would be nonpolar covalent bonds. If we have above 0.4 to 1.7, we're going to have polar covalent bonds, which means that the electrons are shared unevenly. And then if it's more than 1.7, then this would be an ionic bond. And so again, these are more the character of the bond. So is it completely transferred like an ionic, or are they just being shared unevenly for a polar covalent bond? What it kind of looks like is this. So again, that ability of the electron or the element to attract electrons. And so it kind of looks like this, where we are having the polar bond, or rather the nonpolar bond, is even. And so this is all equal, shared evenly, an even tug of war. Versus if we have a polar covalent bond, where now the electrons are going to be shared unevenly. And so then we have a negative side and a positive side. So let's go ahead and practice looking at electronegativity. So is the bond formed ionic, polar covalent, or nonpolar covalent? So go ahead and pause and see what you think. So if we look at these, what we find is that we have strontium, which is going to be electronegativity of 1, versus fluorine, which is 4, and so fluorine's going to hog those electrons. It would be more negative, and strontium would be positive. This is ionic, so they are fully positive and negative because the electron is transferred. If we take a look at nitrogen and chlorine, the electronegativity difference is 0, and so it is nonpolar covalent, meaning that it would share evenly. Finally, if we look at oxygen and nitrogen, we'd have a 0.5 difference, and so we would have a polar covalent bond because the electrons are not shared quite evenly. So whenever we have an uneven sharing, then we have what we call a dipole. This is going to be an uneven distribution of charge. We can also talk about this as polarity. When we talk about a dipole or polarity, we can refer to a bond dipole, meaning is it a polar or nonpolar bond, or rather, if we have a dipole, then it would be a polar bond. Or we can have a molecule dipole or molecular dipole, so is it a polar molecule? What you see in these examples is you see that fluorine, for example, is going to be hogging the electrons, and so it's going to be negative, and this is because of a big electronegativity difference. The same thing is true if we have a bond between oxygen and hydrogen. Oxygen is going to hog those electrons, and it's going to pull the electrons towards itself and become more negative. When we look at electronegativity, it's going to impact the polarity of bonds, and we'll discuss how this impacts then the molecule polarity based on the shape of the molecule.